And even back in the late 70s, we could see with the Voyager data that something curious was going on with Europa. And over the course of the past several decades, we've now come to learn and appreciate that the outer solar system has got a small fleet of ice-covered worlds.
On November 5th, 2018, Voyager 2 crossed a boundary no human-made machine had examined with a working plasma instrument. Nearly 18 billion kilometers from Earth, it moved through darkness beyond every planet. Then the environment around it changed. The stream of charged particles flowing from the Sun almost disappeared. Galactic cosmic rays rose sharply. The surrounding magnetic field shifted. Voyager 2 had crossed the heliopause, the outer border of the enormous bubble created by the Sun, and entered interstellar space.
The spherical ball that is the Sun,
Right.
the oblate spheroid that is the Sun, we speak of an edge, but that's an edge made of gas.
Right.
Okay?
How do you even have that?
That's my point. It's like Earth's atmosphere.
Scientists had expected this moment for decades, but not what the spacecraft measured. The boundary was sharper, the plasma hotter, and the pressure outside the heliosphere stronger than leading models predicted. 5 scientific teams spent a year studying the data before publishing 5 connected papers. Voyager 2 had not discovered that the heliopause existed. It discovered that the heliopause did not behave the way scientists thought it would.
With Voyager 1 and 2, it turned out the configuration of the solar system was just right, so that you could just get multiple planets in a row and escape into interstellar space.
That's very cool.
The real edge of the solar system. The solar system is often pictured as ending around Pluto. Physically, Pluto is nowhere near the Sun's true border. The Sun constantly releases the solar wind, a stream of charged particles moving outward. With the Sun's magnetic field, it inflates a vast region called the heliosphere. Every planet, Pluto, and many objects beyond remain inside this bubble. Eventually, the solar wind can no longer push against material between the stars. Where these pressures meet is the heliopause. Inside it, the Sun dominates. Outside it, the plasma, particles, and magnetic forces belong to the galaxy. Reaching this border took Voyager more than 41 years. Launched in August 1977, it passed Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. After completing the only close visits ever made to Uranus and Neptune, it continued outward for almost 3 more decades. Then the readings changed. Voyager 2 became only the second spacecraft to enter interstellar space, following Voyager 1, which had crossed in 2012. Yet Voyager 2 carried something its twin no longer had: a functioning instrument able to measure the plasma directly. The instrument that survived for 4 decades. Voyager 1 reached the heliopause first, but one of the instruments most needed for that moment had failed decades earlier. Its plasma science instrument stopped operating in 1980, 32 years before the spacecraft entered interstellar space. Researchers were still able to study Voyager, ones crossing through its magnetometer, cosmic ray detectors, and other surviving equipment. Those instruments confirmed that the spacecraft had entered a new environment, but they could not directly measure every property of the plasma surrounding it. Scientists had to estimate conditions such as plasma density and temperature by combining secondary readings rather than observing them directly. Voyager 2 offered a rare second opportunity. Its plasma science instrument had been built in the 1970s and had already survived 4 planetary encounters, intense radiation, extreme cold, and more than 40 years of continuous travel. Yet when the spacecraft finally reached the heliopause, the instrument was still functioning. That meant Voyager 2 could directly measure the temperature, density, and speed of the plasma before, during, and after the crossing. Instead of reconstructing the event from indirect clues, researchers could watch the physical environment change almost in real time. This made Voyager 2 far more than a second spacecraft following the same route. Its measurements filled the most important gap left by Voyager 1 and gave scientists the clearest physical profile ever recorded of the Sun's outer boundary. And almost immediately, that profile began contradicting the models. A border far sharper than expected. Earlier models described the heliopause as a broad transition zone where solar and interstellar plasma would gradually mix. The solar wind was expected to slow, weaken, and blend into the surrounding interstellar material across a large distance, much like 2 bodies of water merging slowly rather than meeting at a fixed edge. Voyager 2 recorded something much more abrupt. On November 4th, 2018, the spacecraft was still moving through the heliosheath, the turbulent outer layer of the heliosphere, where the solar wind had already slowed considerably. By November 5th, its instruments were clearly detecting the interstellar medium. The change happened in less than a day of travel. Solar wind plasma dropped away, while galactic cosmic rays increased sharply. The particles on one side of the boundary were unmistakably connected to the Sun, while those on the other side belonged to interstellar space. Researchers later estimated that the main transition layer was narrower than 0.06 astronomical units. In everyday terms, that still sounds enormous. But compared with a heliosphere extending for billions of kilometers, it is an unexpectedly thin dividing line. The heliopause was not a soft fading of the Sun's influence. It behaved more like a compressed and active frontier, held in place by the pressure of 2 very different environments pushing against each other. Hotter plasma and a magnetic wall. The next surprise appeared immediately outside that boundary. Models had predicted that the nearby interstellar plasma would be relatively cool, quiet, and uniform. Voyager 2 instead found plasma that was hotter than expected and whose properties changed as the spacecraft moved through it. At the same time, Voyager 2's magnetometer detected a region of unusually strong magnetic pressure just inside the heliopause. Researchers called it a magnetic barrier. This barrier appears to play an important role in controlling cosmic rays. These are extremely energetic particles produced by violent events across the galaxy, including supernova explosions. Many travel at close to the speed of light, and prolonged exposure can damage living cells, spacecraft electronics, and astronauts beyond Earth's protective atmosphere. The heliosphere already blocks or redirects part of this radiation before it reaches the inner solar system. Voyager 2's measurements suggested that the magnetic barrier is one of the places where much of that filtering occurs. Its increased magnetic pressure can disturb the paths of incoming cosmic rays, slowing their inward movement or redirecting them away from the planets. That makes the barrier more than an unusual magnetic feature. It is part of the shield separating Earth and the other planets from the harsher radiation environment of the galaxy. Scientists already knew that the heliosphere offered protection. Voyager 2 showed that this protection was concentrated in active layers, shaped by magnetic pressure, and influenced by conditions on both sides of the heliopause. One bubble, two very different crossings. Voyager 1 and Voyager 2 did not leave the heliosphere through the same region. Voyager 1 crossed in the northern solar hemisphere, closer to the direction in which the Sun moves through the galaxy. Voyager 2 crossed in the southern hemisphere, nearer a flank of the heliosphere. If the heliosphere were a nearly perfect sphere, both probes should have encountered broadly similar boundaries. They did not. Voyager 2 passed through a thinner transition and measured different plasma conditions, along with a stronger interstellar magnetic field. Curiously, both spacecraft reached the heliopause at roughly 120 astronomical units from the Sun, even though they crossed 6 years apart and during different levels of solar activity.